First, in the context of data of objects, so I will show you how to implement, in fact, linearizability, the most known mechanisms to implement it, and then I will present you a novel mechanism to implement linearizability, which, differently from the more typical algorithms or protocols, it provides not only fault tolerance, but also gives us better scalability of performance. And from that, I'm going to show you how we can go to a database replication protocol. Okay? So, just like as yesterday, if you guys have any questions, don't hesitate to interrupt me. So the first thing you have to do, so actually the way I'm going to do this is by first presenting a generic functional model. So this is one way to reason about the replication protocols, which, as far as I can tell, you can capture any replication protocol that I have seen so far. And it's very general. It decouples replication protocols in several modules. And depending on the particular protocol, it may have some of these modules, may have all of them, or may iterate through some of the modules. I think it helps us understand how the protocols work. And then I'm going to show you, I'm going to talk about two very well-known replication mechanisms, which are primary backup, probably the oldest replication technique that has been used, also called passive replication, and then active replication, which is also known as state machine replication, introduced by Leslie Lamport several years ago. And then finally, I will conclude this part here with this novel mechanism, which I call multi-primary passive replication. Okay? So let's have a look at the model, so this framework. But before we even get to that, I should tell you a little bit more about our model considerations. So the idea here now is that we're going to talk about algorithms. And in order to talk about algorithms, I have to specify some more things that I didn't specify before when I was talking about consistency criteria. So there is a set of processes. So these are the agents that perform the activities, that execute steps. And as before, there are two kinds of processes, clients and servers. Now, I'm going to focus on communication, on systems that use message passing communication. So if two processes, two clients or two servers want to communicate, they can exchange messages. This is different than, for example, a shared memory system, where several processes, they can share information by having access to a common memory. I'm not considering this case. And in case of, so I'm going to consider failures as well. After all, the whole discussion about fault tolerance is to tolerate failures of some of the processes. But we are going to concentrate on crash stop failures. I'm going to say a little bit more about these failures later. But I can tell you right now that we are not considering Byzantine failures. So maybe some of you know Byzantine failures means I can tolerate any arbitrary behavior of my processes, or some of the processes. So there are replication protocols that address this kind of failures. These are failures that are much more severe than crash stop failures, because a process doesn't simply stop processing, but it also can do crazy things like sending messages that it was not supposed to send. So we're not going to consider those cases. I would be happy to talk about this if you're interested, but that's not the goal of this tutorial. So here's the generic functional model. It separates, basically decomposes any replication mechanism in 5 phases. And it's pretty generic, as we're going to see. And the idea is that being so generic, we can characterize any replication protocol. As I said, I haven't seen a replication protocol that does not fit into this classification. So we have a client, several servers, and there are 5 phases. In the first phase, the client submits a request to a server, or to several servers. It depends on the particular protocol. But the first thing that must happen is the servers must receive the request from the client. In this picture here, I have one arrow going from the client to server 1, straight line. It means, for example, that maybe some protocols, the client contacts only one server. Now, there are also 2 other arrows with dotted lines that reach servers 2 and 3. So in this case here, to illustrate that in some protocols, you could imagine the client sending a request to multiple servers, not to a single one. Now, the second phase is a server coordination. Not all protocols have this, but some of them have. So it means that after the request has been received by one or more servers, the servers, they interact to coordinate their operations. For example, if two clients submit conflicting requests, that would be the time when the servers will decide which request to execute first. Not all protocols have this phase, maybe surprisingly. And then there is the execution of the operation itself. Here I show, so I'm representing this by this circle with the picture inside. So this basically means that each server is executing, so it's executing the request that was sent by the client. Okay? And in the picture, all servers execute it. As we're going to see later, not all replication protocols require all servers to execute the request. Finally, some protocols that rely on some agreement phase after the execution of the operation. And here is, so this is, it was typically introduced to capture optimistic protocols. An optimistic protocol doesn't try to synchronize the access of the servers to the data. It lets servers, clients execute their operations, maybe conflicting in different servers. But of course, if two operations conflict and there was no coordination in the beginning, you may end up with an inconsistent state, right? Because, for example, if two clients are submitting requests to withdraw money from a common account, they may just withdraw more money than there is in the account. So somehow there should be some verification here to make sure that the two operations are not going to lead to an inconsistent state. So typically protocols that are optimistic, protocols that don't have a server coordination, they check at the end of the execution whether the state of the system is consistent and if the two operations can be accepted or not. Some protocols don't need this agreement coordination. And finally, there is the part where the server receives a response. Right? Since the client receives a response. Since you submit the request, it expects to receive a response at the end. This can be an acknowledgement, or can be, I don't know, the value of some read operation. Okay, so that's very generic. Now let's look at a particular replication technique and see how it plays into this classification, this framework. So passive replication is also known as primary backup replication. How many of you have heard of primary backup replication? Okay, a few. So if you guys ever try to replicate some server, chances are that you used something similar to primary backup, because that's the most used mechanism. The idea is very simple. In its simplest form, there are two servers. There is the primary, which executes all the requests, and there is a backup. If the primary fails, the backup takes over. Now, this is simply said, but in reality, if you look into details, and if you want to implement, if you want your prime backup mechanism to guarantee linearizability, then things are not as simple. It turns out that many of these prime backup solutions, they do not give you linearizability, they give you something else which is weaker, sometimes not even very clear what it is. So we are interested here in primary backup replication that ensures linearizability. Okay, so what does it take to get this kind of protocol? Well, first I have to be very strict about the failure model, more strict than I was in the previous slide. In addition to ruling out Byzantine servers, I have to tell you more about how failures are going to be detected in my system, right? So again, a failure here means that one server stops executing, but it does not produce incorrect information during the time it is executing. So we are going to consider the phase-stop failure model. This basically means a number of things. The first one is a process follows its specification until it crashes. Okay? A crash is detected by every correct process. So a correct process is a process that does not crash. And correct processes, they detect the crash of faulty processes. But the most important assumption is this one here. We assume that no process is suspected of having crashed until after it actually crashes. Okay, so this means that the failure detection mechanism is perfect. It does not make mistakes. You may be wondering why it would make a mistake. I can tell you right away. Usually the way to detect failures, the most used mechanism to detect failures, is to exchange heartbeats. So a heartbeat is nothing more than a small message that a service keeps sending to the other servers to say, I'm still alive, I'm still processing. So they keep sending these heartbeats as short intervals. And as long as you receive the heartbeats, you believe that the server that is sending them is still operational, and then you don't suspect the server. Well, it turns out that if you miss a heartbeat, right? Then you suspect that the server has crashed. But it may happen that the server is sending the heartbeats. It gets too busy doing other computation, doing some heavy load computation, and it gets delayed a little bit when it sends the heartbeat. Or it may also be that the heartbeat is lost in the way because there are too many messages in the network. Then, in these two cases, either a lost heartbeat or a delayed sending event, the receiver may falsely suspect that the first server has crashed, while in reality it has not crashed. It's just that it was a false suspicion of a crash. So we do not tolerate this kind of behavior in this part. I'm going to show you next algorithms that do not make this assumption. It's a strong assumption, but it's an assumption that we're going to use to make sure that our prime backup replication mechanism guarantees linearizability. Okay. So having detailed the model, let's have a look at the algorithm. And it's quite simple in reality. It doesn't have phase 2. Right? There is no coordination among servers. There is one primary, and there's a set of backups. So in this picture here, since there are 3 servers, I chose server 1 as the primary. And the other 2 servers are backups. All requests must be sent to the primary. Both reads and write requests must be submitted to the primary. So it's the only one that is allowed to execute the requests. So the way it goes, the client sends the request, or several clients, like if you generalize this case here, they send the requests, and the server one, the primary, executes the requests in the order in which it receives them, right? So there is a total order on the receipt of requests. So here I'm showing that this, so that the primary is executing the request, and then in the agreement coordination, what happens is that the server, the primary, sends the results of the computation to the backups. It doesn't send necessarily the command that was executed here, but it sends the new state. What is this? For example, if the operation is increment variable x, so increment variable x is what is sent by the client. The primary computes the new value of x, and then it sends to the other servers, to the backups, the new value of x, not the command increment x. The backups, they receive this, they install the change, they update their local state, and they reply to the primary. As soon as the primary receives a reply from all the backups that it does not suspect, like if a backup can also crash. So as soon as the primary receives a response from all the backups that do not crash, it sends a response to the client. Yes, you must send. So this response here basically means I have the new state, I'm going to apply it. Now, so I'm fine with this request, we can go ahead. It must be after this response has been received and safely stored. Right? So this has to be because maybe if the primary fails, you don't know where how long it managed to execute. So if you do this, you know that it managed to execute as many requests as it sent to the backups. Right? So it's pretty simple. If a primary crashes, then one of the backups is going to take over. So you can totally order all the servers based on their IDs, for example, and this order is going to tell which server is going to be the next primary in case the primary crashes. So I remind you that we are using a perfect failure detection mechanism. So it means that if a backup suspects the primary, it's because the primary really crashed, right? There's no false suspicion. So there is no risk that some server suspects that the primary has crashed while the primary is still executing. If that happens, you'd end up with more than one primary, which may be actually problematic, right? Although there are solutions to this kind of problem, but they are much more complicated. Okay, so that's the idea. It's quite simple. So summarizing, it requires perfect failure detection, which is going to ensure that only one primary exists at all times. The failure of a primary is detected by the backups, and eventually one of the backups replaces the failed primary. Okay? So that's the main idea. Now let's look at another mechanism that gives us also linearizability, right? So the idea here is, this was proposed by Leslie Lamport in 78 in one of the most fundamental papers in distributed systems. Time clocks and the ordering of events. How many of you have read this paper? 78 paper. At the time when Communications of the ACM published solid stuff. Oh, they got better now. So I saw a hand. Did you read this? Time clocks and the ordering of events? Okay, good. So this paper has many things. One of them is the idea of state machine replication. Right? So the idea is quite easy actually once you are presented to it. And it does not require strong failure detection. As I'm going to show you here, it assumes something that's weaker. It requires the crash failure model. So what this means is the following. A process follows its specification until it crashes, just like before. So what's behind this statement here is that I'm not considering Byzantine failures. Okay. The second thing is a crash is detected by every correct process, just like as before. So far there's no change with respect to my previous model. If a process crashes, eventually you want to know that this process has crashed. Now the difference is the third bullet. Correct processes may be erroneously suspected. As I said before, it's almost inherent to the way these things are implemented. Sooner or later you may end up falsely suspecting some server. So this failure model here accepts that, right? So it means that my algorithm, the algorithm that I'm going to introduce to you, it tolerates this kind of behavior. And it still ensures linearizability. How can it do this? Oh, it's more complex than the previous one. So to hide the complexity, because that could actually be the subject of a lecture in itself, how to provide the means to implement active replication under this failure model here. I'm going to very briefly explain a group communication abstraction, which is called atomic broadcast by some. Sometimes it's called total order broadcast. So it's a very powerful communication abstraction, and it's built on top of our message passing system. Okay, our simple underlying message passing system. It defines two primitives. So primitives are basically, you can think of primitives as the API that this abstraction provides to the applications. So broadcast M says that I'm going to send a message, I'm going to broadcast a message M to a set of servers, receivers. And deliver M is the event that happens at the server that received the message. Is how they get to know that there is a message that has been broadcast. And this abstraction here, it guarantees a few properties. The ones that are of interest for us are agreement and total order, which I'm going to specify intuitively. I'm not going to give you any formal definitions of these properties, but there are definitions that are formal versions of these properties. The first one is agreement. It says that either all servers deliver the message or no server delivers it. Okay, so I don't have a situation where one server delivers the message and the others don't because, for example, the sender failed during the submission process. So there is there are protocols that implement atomic broadcast, they account for such cases, right? So they guarantee agreement. And they also guarantee total order, which means that any two servers deliver messages M and M prime in the same order. So if two messages are broadcast by any sender, all these messages are going to be delivered in the same order. So it may sound like it's a simple abstraction, but it turns out that it's very powerful. It's so powerful that it allows me to implement linearizability in a failure model like the one I presented before. So I don't have time to go into details about atomic broadcast, but I'm going to give you just an idea of what it means, this abstraction. So for our representation, or graphical representation, I have thick lines to show that this is atomic broadcast. Right? This is a message that has been, so here I have two messages, M and M prime, and these messages were broadcast by the clients. Right? The arrows are thick to show that it's not a simple point-to-point message transmission. There is more going on that's going to be implemented by the module of the system that implements atomic broadcast. And I don't care how this is implemented, but it could be something like this, for example. So you can assume that there is some library that exchanges messages among the servers to give the properties that I need, total order and agreement. But I won't spend any time discussing these things. So that was actually part of the theme of the other tutorial that I gave here a couple of years ago. There are many tens of algorithms that implement these properties here, right, in different environments. But I'm just going to assume that there is an algorithm, I'm using it. And I will not represent how it happens inside. I'm just going to use the thick lines representing that this is atomic broadcast. Okay? So if you want to have an architectural view of the system, you can look at it like this. So it is the network. Network is the underlying communication system. Actually, it makes up for our assumptions about how processes communicate. I'm assuming that it's message passing communication, which basically means I'm assuming that there is some layer that gives us communication through the means of a send and a receive primitive. And then I have my group communication layer, which sits on top of this network layer. And this group communication layer implements broadcast and deliver. And on top of this group communication, I have my application, which here for us means our replication protocol. Okay? Our replication protocol is going to use the broadcast and deliver primitives. You may also use send and receive in some case if you want to do point-to-point communication, right? So here's active replication using atomic broadcast. It is straightforward. The only thing that happens is, so it doesn't have phase 4. There is no need for any agreement among the servers after the execution of the command. The way it goes is the client picks one of the servers, selects one of the servers, and contacts the server and sends the command to be executed. The server atomically broadcasts the command. So that's what the thick line means. So whatever command it received from the client, it broadcasts to all other servers. Right. So once again, this atomic broadcast is going to give me two things. Agreement. If one server delivers the message, all the other servers are going to deliver the message. And total order. For any two messages that are broadcast, the receivers are going to deliver the message in the same order. So it turns out that this is enough to get linearizability in a weaker failure model than the one we saw before. So what happens, there's a phase 3. Each server, upon delivering this command, it locally executes it, changes the internal state. And then all the servers, they reply to the client. The client only has to wait for the first answer, and then it knows that its command has been executed. Okay? So that's the general idea of the technique. Now I have to look at some detail. The first one is, it assumes, right, that if each server executes every request in the same order, they are all going to have the same state after processing each command, right? So this basically means that I'm assuming that the execution of each command is deterministic. So how limiting is that? How limiting is this assumption that my commands are deterministic? What things I cannot do? Load balancing. Can you be more explicit?
Have the server execute the commands, just the same commands, applies to that.
Oh, I see. Okay, that's a good point. It's actually it's a weakness of active replication in general. I'm going to get back to that. But right now, I just told you that it assumes deterministic execution, right? So it basically means that if I provide a server with each server with the same sequence of commands, they're all going to end up in the same final state. So for example, if I depend on things like, if my commands depend on things like the time of the day, right, then I may run into trouble, because the clocks that run in each one of the servers, they may not be perfectly synchronized. If two servers try to get the time of the day, right, they may not result in the same value, which means that my execution is not going to be deterministic. And even though they're executing the same commands, they may not end up in the same state, right? So I cannot do things like this that would violate my deterministic assumption. So there are ways around this limitation, but there are other limitations that are also severe. For example, I cannot execute these commands here, so the execution of these commands cannot be multi-threaded, right? Because if I start executing these things with several threads, I may run into situations that are going to be different in the different servers because, well, thread scheduling is not something deterministic. So this is another limitation. Usually, I have to execute all these commands here one at a time, right, sequentially, to make sure that the execution is deterministic. So all these are known problems. They have been known for me for many years, and there are workarounds. But these are, in essence, fundamental limitations of the approach. Okay. So having said that, let me try to give you a little bit the intuition of why this thing works. Because it's a quite nice technique, and it gives us linearizability, which is a very strong property, as we saw yesterday, right? So let's see why it gives us this. So let's get back to our picture here. Let's see if you guys are awakened. Is this execution here linearizable or not? No. Good. So why it's not? Yes. It goes back to our swapping of operations, right? So here it returns 0, and there it wrote 1, and they do not overlap. So this is not a linearizable execution. Okay. So what we're going to do is, let's try to implement this using active replication, and let's see why such an execution would not be allowed by our active replication, right? So let me go back here just to remind you. So the way it goes is for each client request, it chooses a server, and the server broadcasts the command. Okay. So let's see. Yes. Yeah, all servers, they reply back, and the server is happy with the first response because they are all the same. Right? So let's see how the execution would proceed. Initially, I'm assuming that each server starts with the same initial state. Otherwise, things are not going to work, right? So they all have the same value of variable x, 0. So here in this picture, in this execution that I chose, client C1 chose server S2 and send its command. The command is write x1. So this server here, it broadcasts the message to all the other servers. Notice that I'm forcing things a little bit here just to emphasize that the system is not synchronous. Messages are going to be delivered at different times. So it took quite a lot of time for this message here to be delivered by server S3, while in these two servers here, it was delivered very quickly. Maybe you can assume that it depends on the environment where the system here is deployed. You may imagine that these two servers, they are near each other. This one here is very far away. Right? So it takes a little longer for the message to be delivered. But it's an atomic broadcast. Right? So no matter what, the order must be preserved and agreement must be preserved. Okay? So each server receives the request and locally executes it. So locally executing means they all set the value of their x variable to 1. Okay? And they all reply to the server. I'm assuming that the first reply that reads the client is coming from server S1, which is not even the server that was contacted, right? But it doesn't matter. The client is happy with the first reply because, again, they must be all the same. Now let's see what happens with the second operation. So client C2 happens to contact server S3. It sends its read operation, which is going to be broadcast. So it's broadcast, and let's assume that server S3 delivers the message and sends the reply back. So by the time it delivers the message here, the value of x is 0, right? So the value it returns to the client 2 is 0. So you guys just said that this is not acceptable, right? So why is this? In which way is this execution here violating active replication? Different orders. Right, so what's wrong in this picture is that servers S1 and S2, they delivered first the message from client 1 and then the message from client 2. But server S3 delivered first the message from client 2 and then the message from client 1. So this is not allowed because it's violating the total order property of atomic broadcast. So I have to deliver this message here after I deliver this message here and have treated all the requests that this message here carries. So in reality, the correct picture is this, because now our servers deliver the two messages in the same order, right? Now here it's easy to see that once the request from client 2 is delivered, server S3 now has the new state and can reply back to the client, right? So what's going to happen is, from the client's perspective, its read command is not going to finish here, because server S3 is going to send the request here, so it's going to be stretched over here, as the animation shows, and then it returns 1, which is the right answer. Okay, so that's just to give an idea of how it implements the linearizability. So total order is a pretty powerful abstraction, right? Any questions so far? Okay, so I just present to you two replication mechanisms, active and passive replication. These were mechanisms designed for object replication, and they target fault tolerance only. So why is that? So why they are not good for performance? Well, because in active replication, all servers execute all requests, right? Every server must execute every request. So that's the problem with active replication. If you want to get good performance, or if you want to get scalability. Now, the problem with passive replication is that only one server executes all requests, no matter how many servers you have. So let me give an example of why this is not good for performance. So if you want to performance, you can interpret it in many ways. I'm focusing here on scalability, really. So if you want to have more clients, right? If you want your system to be able to serve more clients, what you'd like to do is when I add more servers to your system, right? Well, it turns out that neither active nor passive replication are going to give you that. The fact that you add more servers to your system is not going to give you more power to handle more client requests, for the reasons that are stated here. If all servers must execute all requests by adding more servers, you're not allowing more clients, right? You are tolerating more failures, but you are not allowing more clients in your system. And in the case of passive replication, it's also pretty obvious, because since no matter how many servers you have, only one can treat all requests. So you can keep adding servers to your system, you're not going to get more clients served per time unit. So this is the fundamental problem with these techniques. Now let me introduce a variation of these two techniques that gives us not only fault tolerance, but also high performance. And this technique is, so I call it multi-primary passive replication. So it's like, but you can also think of it as optimistic active replication. So the idea is, it was designed for both fault tolerance and performance. It does not require perfect failure detection. So this means that it has the same resilience, the same assumptions about failures as active replication. Okay? But it has better performance. And the better performance is coming from two aspects of this technique. The first one is that we distinguish read from write operations, which was not the case with active replication. Every request, regardless of what it did, was treated in the same way. Now we are going to distinguish these two, because they're different, fundamentally different. One changes the state of the system, the other doesn't change the state of the system. And the other difference, so this first one is quite simple, actually, could be applied to active replication as well. The second one is a little bit more complicated. Only one server executes each request, right? Differently than active replication, where every server executes all requests. So that's why I call it multi-primary passive replication, because in passive replication, only one server executes the requests. So here, I also have only one server executing the requests, but not necessarily the same server. So let's go in steps. So I said that we are going to distinguish read requests from write requests. So that's the first feature, so the first characteristic of this replication technique. A read request, it is first broadcast to all servers, okay, just like active replication. But it's executed by only one server, and the response is sent back to the client, okay. So I still have to broadcast it, otherwise I may not get linearizability. So I must broadcast read requests, otherwise I do not get my strong consistency criterion. Right? But only one server executes it. Okay. So here you can already see how I can get better. I can serve more clients by adding servers, right? Because since read requests are executed by only one server, if I have many servers, I may be able to serve more requests because I can distribute these requests among the servers. Although I haven't changed the way update requests are treated so far. So that's the second part. So for write requests, things are a little bit more complicated. The client chooses one server, right? And this server is going to execute the request. The server that's chosen by the client. And once the server has executed the request, it takes the new state, right, the state that was produced after executing this request, and it broadcasts it to all servers after it has executed it, not before, as with active replication. So what you broadcast is the new state, is not the command. And then what happens next is, so the servers are going to deliver the new state. So if the chains that this command produced, they are compatible, at loose sense so far, I'm going to make it more precise in the next slides. So if the chains that were caused by this command here, state chains, they are compatible with the previous states that the server installed, then the command is accepted, right? And the new state is installed. So the new state is the state of the server changed to reflect the new command. And the result of the request is returned to the client. So if the chains are not compatible, right? If the command that was executed by the client is not compatible with what the server did in the past, then the request is rejected and must be re-executed. Okay? So that's a general idea. But it's kind of loose. I have to specify there what compatible means, right? And that's what I'm going to do next. Well, before I do that, let's go through the protocol and make sure that we understand how it works in general. So here I have a write request that is sent by client 1. Client 1 chose server S2. He sent its write request. It was executed here, right, by server S2. And the new state, the changes made by the command, they are broadcast. So that's why I show this part here using my thick lines, which represent atomic broadcast. So it broadcast the new state. It was delivered by all the servers. And let's assume that this state here is the change that it contains are compatible to the current state of my servers. In which case, they all apply the change, and one of the servers replies back to the client. Okay, I'm assuming here that server S1 could be any server. Later on, client 2 does a read request. So read requests are immediately broadcast to all servers, but only one server executes it. So only one server retrieves the value of X and returns the answer to the client. Okay.
How is that we use feature? Feature houses right and feature.
Yeah, I'm not specifying that. You're free to choose. It can be like, I don't know, based on some random number. A server randomly decides, the client randomly decides which server is going to be used. You can have some load balancer interface in the system. It can be whatever you want. It doesn't change the technique. Okay, but that was a simple case, right? Let's look at a more interesting case. Let's assume here that let's see how two writes are treated in this system. So the first one was the first operation I had before, write X1. So there is a state change executed by server S2, which broadcasts the new value. Okay, whenever the servers receive it, they install and they reply back to the client. Now, in the meantime, right, client C2 decided to also change the value of X. And what it did is, just like there, it chose server S1, right? It sent the request to server S1, which processed it and then broadcast the changes. Now, it broadcasts the change, so the change here is x2. And let's assume that it managed to do it more quickly than client 1. It was delivered by all the servers. This new state was installed. It was x2. And then later, the message with the state x1 was delivered, and it was changed like this. So the final state of my variable x is 1. So is this execution here linearizable? Why not? Yeah, the total order applies with respect to the atomic broadcast. So they all deliver in the same order. First this, and then this, first this, and then this, and so on. So the total order is... This execution here, it's a perfect execution of atomic broadcast. Now the question is this... so we know that the final value of my variable is x1. Right? Is this linearizable? Yes, it is, right? Because my two writes, they overlap, so I can order one after the other the way I want. Even though the first write there was issued before the second one, the two operations overlap. So that's fine. But this is a tricky execution. It should be this mechanism here should be generic. It should apply to any command, right? Not only simple writes. So let's see what happens in my system if I change my operation. Right? Small change. I change it from write x1 to increment the value of x by 1 and increment the value of x by 2. Right? So all the rest is going to be the same. If you guys are not convinced, you can go through the execution. So the increment x1 was received by the server here during the time when the value of x was 0. Right? Execute increment 1 means the new state is 1. And then it's broadcast. Now, in this case here, the increment x2 was received by SU1 when the value of x was 0. So it's incremented, the new state is 2. And it's sent to all the others. Right? But now, is this execution here linearizable? Why not? Yes, it doesn't respect the semantics of my operations. Because there is no way I can reorder this, right? I can place this operation here before this, or the other way around. The final result cannot be 1. What must be the final result? It must be 3, right? So there is something wrong here. And what's wrong is basically what I didn't tell you about this. What it means for two states to be compatible. So it turns out that when I deliver the second message here, right, and I check to see whether this state here is compatible with what the servers have done, the answer is no. This message here, this operation here, the new state is not compatible with what was done before. So it cannot be accepted. Do you get the general idea? Now let me tell you a little bit more what I mean by two states being compatible or not. Right? Okay, so this is addressed by the second part. If the chains are compatible with the previously installed states, then a new state is installed. Otherwise, it's rejected. So it must be re-executed. And that's how we are going to avoid that case. So let's define compatible states, right? And for that I have to give a little bit more background here. I have to introduce a few terms. So let's assume that SI is the state at some server N, right? Before it executes some operation alpha. It can be any operation. It can be the write, can be the increment, can be whatever you want, right? And SI prime is the new state that's generated after executing alpha. So I represent this picture as this. So if this is the initial state, I execute alpha, I get this second state here, SI prime, okay? Now we can look at a server as a history of states. Right? The very first state S0, the initial value, and then a composition of states, each one deriving from the previous, upon execution of a command. And so I say that state SI prime is compatible with my history age, my sequence of states, right, of all the states in the server, if one of two things happens. First, So here, the last state in my history, age is Sj. Okay, so the sequence of states where the last state is Sj. So Si prime is compatible with Fj with age if the last state in the history is the state that precedes Si prime. Right. This basically means that Si prime was computed based on Sj. So it certainly is compatible. Because it means that Si prime was Sj plus some operation, right? So that's the simple case. In other words, there was no concurrency. There was no conflicting requests being executed simultaneously. Now the second case is a little bit more complicated. So I say that my Sij is compatible with my history here, even if it does not derive directly from this state, right? If whatever command alpha did, right? It does not read any variables that were modified and in the states that succeed Si. So Si prime was derived from Si. So here I can have Si plus 1, plus 2, etc. until I get to the last state in my history. Right? And I try to apply Sj prime after Sj. So if none of these states here, right, were read by my operation, then Si prime is also compatible with the previous states. Let me show you this in a picture. It's much easier to understand. So here we have server N, and it executes the write operation. Okay, and the write operation basically it had so the state of the server is composed of 3 variables: x, y, and z. And I execute the write of x, so I change it to 8. And I create a state Si prime. Right? Change one operation. So, and then I broadcast the command. So in case A, so there is another server N prime that currently it is at its current state is Si when it delivers the message with Si prime. So in this case here, server N prime, it realizes that the new state Si prime derives directly from its current state. So it is compatible. Actually, alpha was executed in the same state that it is currently now. So you can simply accept the changes and install them. Because, well, what's being proposed, the new state derives directly from the state it has. And then generates the state Si plus 1 by applying so the new values, which is the value of x. So it keeps the others as they are and changes the value of x. Okay, so that's the easy case. Now the not so easy case is case B, where some server N prime, it also passed through this state Si, right? But by the time this command here arrived at server N prime, other commands arrived, right? Write x3, write z5, and in these commands here, they caused the state of N prime to advance, right? So, and then by the time the message of Si prime arrives at my server, there are other states that have been changed the current state of my N prime. Now, is Si prime compatible with this state here? So the answer is, has command write x8 read anything that changed in the meantime? And the answer is no, because actually a write doesn't read anything. So that's why our example with writes, it worked out. It was linearizable. Because a write doesn't read the value of the variables. Even though the value of these variables changed, it doesn't read them. So it's still a valid command. It can be accepted. It can generate a new state Sj plus 1 with the new value of x. So in this case here, although the command was executed in a state that precedes the current state of my server, right, it can still be accepted because it does not depend on the states that happened in the meantime. The current state of the server, when the Si prime is received, is still valid with respect to Si prime. Do you get the intuition? So how do you do this, right? How do you implement this in practice? So the way to implement, there are several ways. One way is that each command must register all the data items that it read, which is called a read set. So when a server executes a command, you should also compute the read set of this command. You should check, when I execute this command here, I read variables x and y, and should send this information to the other servers. So that's one of the implications. You must be able to tell which variables were read. Right? So let's go back to our
Was such a picture even possible? Why our first doesn't have z equal 5 and y equal 3?
Oh, why doesn't have? Because because maybe the server here is a little bit slow and has not received the chains, right? But it turns out that the client contacted the server, but the chains are in the way, but they haven't arrived yet. So it's lagging behind a little bit. But they are going to be received, right? They must be received because otherwise it would violate the total order. But they are not running synchronously, so that's why it receives later. That's a very good question. So let's go back to our case, so the example that doesn't work here, and let's see how multi-primary passive replication solves the situation here. Because as you saw, this is not linearizable, right? So what happens is, at the time the second command is going to be delivered, together in the command, right? So an increment, actually, if you think of an increment, it requires the value of the variable to then add it. So an increment is basically, in our more basic operations, is a read followed by a write. So you read the value of x, you add 1, and then you write the value of x. So you depend on the previous state of x to actually compute the next state of x. It's different than a write, a blind write, which does not depend on the current state of the variable. So an increment depends on the current state, which means that the increment needs to read the value of x. So when my second method here is delivered, right, each server looks at its read set and sees, it depends on the value of x. And then must be able to tell that, but it depends on the value of x that has changed in the meantime. So I cannot accept this second operation. The second operation must be handled in a special way. Now, how it's handled? We can simply return a message to the client saying it's not accepted. You have to reissue your operation. Or as shown in this picture here. So if the clients, they also send the operation, in addition to sending a new state, they also send increment x2, right? If the operation fails, because the new state was based on some value that's no longer valid, so they all execute the operation, just like in active replication. And by all executing the operation, they are all going to lead to the semifinal state, which is x3. Okay? Yes, so this thing here, yes, it only works, right? It only gives us the nice feature that you want, which is basically the scalability, if I don't run too often in cases like this. Because whenever I submit two operations, I have to re-execute them, this is worse than active replication, right? Because in addition to having our servers executing the operation, I also have this initial phase here, which is not serving not doing any good. So it's definitely true. And it is stated here. So in reality, this is an optimistic approach, right? It's based on the assumption that most of the time I won't have situations where one state becomes invalid. It depends on the nature of the operations. And so it may or may not rely on deterministic execution. It depends on how I solve my conflicts, how I solve cases where a new update is not compatible. So if I rely on every server executing the request, then I need determinism. So if I tell the client, resubmit your request, then determinism is not needed, right? Because it's going to be executed by only one server, which is going to send a new state. So there's another fine print here, which is, I'm assuming that installing a new state is cheaper than executing the command. This is true for some operations. It may not be true to all operations. Sometimes the change in the state is as expensive as executing the operation. In that case, I'm not gaining anything, right, by doing this. But in many cases, it's more complex to actually compute the command than to simply apply the chains that were made by this command. Well, why I'm doing this? Because now I can get both fault tolerance and performance. differently than prime backup alone and active replication alone. What this means is that if these assumptions that I showed before are satisfied, right? So if installing the state is cheaper than executing the request, and not and a substantial number of the operations they do not depend on each other, right? They do not read of the other changed. Then by adding servers to my system, I can get better performance. Why? Well, because the operations are the more servers I have in my system, the more operations can be executed, right? Read only because they are only executed by one server, and write operations because if everything goes fine, it's going to be executed by only one server. The others have only to install the changes. So that's the idea. And it turns out that this is now suitable for database replication. Okay, so it means that I can actually use something along these lines here,